Okay. I hope you are all able to see my screen, right? Okay, let's start our today's session. Good evening, everyone. I'm Gangadhar Venkatramana. I'm your teaching assistant now in this Fundamentals of Theoretical and Experimental Aerodynamics course, teaching by Professor Arnav Roy sir from the Department of Aerospace Engineering, IIT Kharagpur. So thank you for taking this course. Today we will see some assignment questions and review of week 1 lectures that you had already maybe gone through the lectures and your assignments of the week 1. So I will just give some overview of what you have learned so far in the recap of week 1 lecture, and then we will solve some questions related to those topics so that it will be helpful for you in solving your present assignment questions. So let's start our session. And okay, so in the session 1, in the week 1 lectures that you have seen many concepts, and you have gone through the introduction to aerodynamics and many problems that you have already seen solved by the professor. And this is one of the important concepts that you are seeing on the slide. This is the standard atmosphere. I can say a graph, standard atmosphere graph. This shows you the temperature distribution as a function of altitude in the standard atmosphere. This was standardized all over the world. So here you can clearly see. I will take the laser point. Let me take a laser pointer. Okay. Now you can see. Suppose we have a standard temperature on the Earth's surface that is at altitude of 0 meters or the 0 kilometers, whatever it is. So you have a standard atmosphere temperature of around 288.16 Kelvin. From that 0 altitude to 11 kilometers, you have the temperature in a decreasing order, and its gradient is A1 equals to minus, this A1 is a, we call it as a lapse rate. So these lapse rate varies with altitude. For this first lapse rate, we have first gradient region. The lapse rate is minus 6.5 into 10 power minus 3 Kelvin. That means this is like this much of temperature, 6.5 into 10 power minus 3 kelvins are decreasing per every meter. If you convert it to the kilometer, 6.5 kelvins are decreasing per kilometer. This is your first gradient, and this is we called as a gradient thermal region. And the second layer is from 11 kilometers to 25 kilometers. Here you have the first isothermal region. In this isothermal region, your temperature is more or less constant and it won't vary. That is around 216.66 Kelvin. Kindly note these values on the graph also, if these things will be helpful for you to solve the questions later on, or also in the today's session also. And after this isothermal region, after 25 kilometers, again you have the second gradient region where temperature increases with altitude here and increases up to around 282.66 Kelvin. And then you have again isothermal region, gradient region, again isothermal and gradient region. So there are 4 gradient regions, and the corresponding values also you can see A4, A3 and A2. So the isothermal values also, isothermal constant temperature values also you can understand here. It starts from 216, 282, 165 and 225. So this is the standard atmosphere, which helps us to understand how like if any clouds are movement, or if a chimney releasing some kind of gases to atmosphere, or an airplane releasing a smoke, or any smoke particles, dust particles that has the temperature and that specific pressure also it has. So these kind of properties, if we know, we can understand whether it will goes to some, it how it will react, or how it will be deal with the atmosphere, whether it will be stable, those smoke particles, or any other particles like that is diffusing in atmosphere. You can understand like the carbon particles, we can easily understand based upon our relations. So this is very crucial for our entire understanding of temperature, or the pressure, or the distribution of standard atmosphere. So along with this, we need to understand few other things. Like we just seen how this temperature is varying with respect to altitude. These calculation of these measurements were done by some balloon kind of experiments. Suppose a balloon tied with measuring instruments, and that balloon will be released into atmosphere, and that will gather the data of this all this temperature and current pressure at that location. So that's how these plots are generally made by the experimentalist. Uh, so let's also see a few things about the topics that Professor had covered in your week 1 session. I will just give you the some important equations that needed for the present session, today's session. So let's see those things. Suppose we just seen how this temperature is varying with altitude. Let's say our gravity G. How this gravity is varying with respect to altitude is also we derived, Professor derived in the classes. So the equation that corresponding to variation of altitude is, I mean the gravity variation with respect to altitude is G equals to G naught times, sorry, R by R plus Hg whole square, where R equals to radius of Earth and Hg is the geometric altitude. So if you are going height normal to the surface of the earth, then the g naught is the, if g naught is the acceleration due to gravity on the earth's surface, this is how your gravity varies with your altitude, that is r by r plus hg whole square. So this is the important equation that you need to understand how g varies with altitude. So this equation clearly shows that g decreases with your height as the denominator is greater. So if your denominator, if this is the thing, we also have one more equation to understand the pressure variation with respect to altitude. That is a governing equation we also called as hydrostatic equation. This hydrostatic equation, how it varies is the pressure dP, we can say, if a small governing equation was derived based upon taking a small elemental volume, and from that elemental volume analysis we found that dP is equals to minus rho g dH g. This dH is a small altitude, and dP is a small variation of pressure with respect to this change in altitude. So this is how the pressure decreases upon increasing the altitude. This is your governing equation, and g is the corresponding height, the gravitational constant at that corresponding height. So this is geometric height, and this is the corresponding gravitational constant. So what this will give us to a one more idea to include the geopotential altitude. Geopotential altitude. How you can define this geopotential altitude means, if you are using this hydrostatic equation as dP is equals to minus rho g dH g, just replace this g with g naught. G naught means minus rho g naught dH. This dH, H is, we can see there is no suffix g. Suffix g represents the geometric altitude. Without suffix, it represents geopotential altitude. So this is the geopotential altitude we have, and these two are equal. Just equate both the things. dHg equals to minus rho g naught dH. You know that g decreases with height, whereas g naught is constant. It is g naught is the value of acceleration due to gravity on the surface, on the Earth's surface. So minus rho g naught dH. So as your g decreasing with your height, this value is also vary. So as you are now making this g naught constant, and the pressure should not vary. That means the resultant value of left and right dp, this dp should not vary. That means there should be a difference between this geometric altitude and geopotential altitude. This is how we are invoking a new parameter called a geopotential altitude. So this is also important to understand. And then this next equation that we need to understand is uh, let me check whether it is, yeah, it is recording. So the next equation is the equation of a perfect gas, or the characteristic gas equation. I can write it as characteristic gas equation. It is very common that you have been learning from your inter or 10th standard, that is P equals to rho RT, where your P is the pressure at that point, rho is the density, R is the universal gas constant, this is the gas constant, and T is the temperature. Sorry. So this is a very important equation that we also called as the perfect gas equation or the characteristic gas equation. And then these are all the important basics before trying to understand this standard atmosphere pressure and temperature variation. Using all these basics now, I mean in the lecture professor framed the equations how the pressure and the temperature is varying with respect to the altitude. Using all these equations he derived that. I will just show you in the next slide what are those equations that we are interested on. So let me write the equation for pressure variation with respect to the altitude. Variation of pressure with altitude. Suppose if you have a pressure at the surface, this is your surface or some known point, any known point P1, and if you want to know at some altitude h, and this is a pressure P, if you want to know this pressure, this is the known pressure and this is the unknown pressure, and consider this region as a isothermal region. In the isothermal region, okay, in this isothermal region, how this pressure varies with the altitude is P by P1 equals to, or you can say, let me use some other options. So P, the unknown value P equals to P1 times, okay, and yeah, let me write, sorry. RT times h minus h1. This is your known height h1, and this is your this is also your known height, that is h, and h1. This is the height at this point is h1, that is you can say it's 0, and this is h. So this is for isothermal region. We already seen from what height and how many isothermal regions and how at what altitudes these isothermal regions are available. So now we understood just how the pressure varies, but how the temperature varies? In this isothermal region, does temperature vary? No, the temperature is constant. You have the constant temperature as T equals to T1. So whatever the temperature at T1, the same temperature is available at T. And then the corresponding density, how the density vary if you say, as from your perfect gas equation, P equals to rho RT. If you divide it by rho 1 RT1, you will get P by P1 itself is equals to rho by rho 1, as T1, T are constant and both are same. R can be also cancelled. So you will get P1 by P1 equals to rho by rho 1. So this is your unknown density. So you can find out with the same equation of this. So that's how your temperature, your pressure and density varies with altitude. Suppose now if we are going to understand how the pressure varies with altitude in a gradient region, gradient temperature region, variation of temperature with altitude in gradient temperature region. Let me go back to the meeting once to see you. Yes, it is. I'm online. I just want to confirm whether, because whether I'm in online or not, or my network disconnected. If something is disconnected, you can uh, okay, is it's recording? We will discuss that, how to let me know, or else if it is connected back, please kindly respond sometime so that I can understand that we are in online and we are discussing it. Recording is done. Yes, we are. I'm in online. Okay. So let's see. Variation of temperature with altitude, that's a gradient temperature region. The same way as we seen how the pressure varies in the isothermal region, we also have the same condition. Let's take the same condition in the gradient region. So P is the unknown pressure in the gradient region, and this P can be written as P1 times T by T1 of minus G naught by AR, where G naught is the your acceleration due to gravity and A is the lapse rate and R, you know, the gas constant. Okay, so all variables, you know that only the T at that height is the unknown again here. T1 is known, G naught is a constant, A and R also known, lapse rate, you know, in the gradient region, that is standard values. And if you don't know the T, again what you need to use is you need to use the lapse rate equation. How it is? T minus T1 by H minus H1 equals to your lapse rate. So this is how you can find out your T. As you know that H and H1 and T1 is also known, you can just find out your T1, sorry, you can just find out your T from this lapse rate value. This is a direct equation. In the same way, if you want to find out your density variation also with altitude, try to use the same equation, this one, that is P equals to rho RT by P1 by rho 1 RT1. Just substitute your T1 T by T1 or the equation P by P1. You just transfer this P1 here and substitute the remaining RHS. Then you will get what you will get, rho by rho 1 equals to T by T1 times minus G naught by AR plus 1. This is also one of the important equation. That's how you can find out the variation of density with altitude in the gradient thermal region. Okay, right. So up to this, then we covered like how to deal with the altitude variation of temperature and pressure and density properties in the standard atmosphere. Now we will see some basics of aerodynamics with respect to the flight. I will just go to a slide that what professor presented to you. Yeah, so let me show you the slide. Are you able to see my screen? Hello? Can you all see my screen?
Yes.
Can you see? Okay. Can you see the flight?
Yeah.
Okay, fine. So this is a flight, a general a schematic diagram of the flight and airplane that you can see. Then the basic understanding of this, you need to see what is the flight condition, whether it is doing some maneuvers. Maneuvers means whether it is rolling or climbing up or descending, acceleration or deceleration. All those things will come under maneuvers. But now every time for our simple analysis, we see the flight is in a study level flight. What is the use of this study level flight? In this study, sorry, use of means it's like most of your flight is in study level. After it's climb up, it will take from the starting point to the destination. It will be in most of the time for long amount of time in the study level. In the study level, the thrust generating by the these are the engines. The thrust generating by the engines T is equals to the amount of drag due to the air resistance on the surface or the pressures drag due to the pressure differences. The drag can be of several forms. You will see how many drags can be seen on an airplane, like pressure drag, skin friction drag, interference drag, all those things you will see in the upcoming lectures. So those all drag will be overcome by the thrust producing by the engines. So if the both forces are getting cancelled, the momentum will not change. So the flight will proceed with the same momentum. So longitudinal forces are done. Now you have the transverse forces or forces in the upward and downward directions. So how those things will be balanced? Every time that you can see due to the self weight, there is self mass, a weight force always acts. Sorry for the disturbance. A self force of a weight will always act towards the center of the gravity, that is W. That is the weight of the aeroplane. This should be balanced by the lift generation by the wings. As flow passes over the airfoil, sorry, as flow passing over the airfoil, you already seen how this lift is generating by some basic principle of understanding. As the airfoil is turning your flow from inlet, what is this, from inlet to the exit. This inlet you are letting your flow in a straight horizontal way as a free stream, but at the exit it will turn like this. As this turn of the flow is required some kind of momentum exchange. That momentum exchange is creating some pressure distribution or the forces generation of the airfoil that will give you the some component of the force in the upward direction. Okay, that lift force should be balanced by, sorry, that lift force is should be sufficient to balance your weight. Okay, so I will go to the slides again. Okay, now we just understood that in a study level flight, lift L equals to weight W. This is very important equation that you need to understand, and you need to remember for your entire course and later also. And then another thing is thrust. The symbol is T and equals to drag D. These two you need to understand. And then let's see some important equations, like how this lift is proportional. Suppose if you have flow, incoming flow, and this is your airfoil, This is the incoming flow. Consider this is the uniform flow coming on to the airfoil. Then the amount of lift that is generating by the airfoil L is equals to, so, or it is proportional to, I can say it is proportional to the dynamic pressure. Dynamic pressure, we have the symbol, we denote by the symbol Q, and the surface area of the wing. Suppose it is a plane form area. Sorry. Suppose it is your plane form area, the top surface of your wing. That surface area is combination of these two will give you the net amount of lift, and that proportionality constant L is CL. CL equals to Q infinity into S. Sorry, L equals to CL into the CL times Q infinity times S. This Q infinity means this is the dynamic pressure. This is non-dimensional lift coefficient, and this is surface area. Okay, so these things are very important, and we can also see the Q infinity is equals to half rho V infinity square. This is the formulation of the dynamic pressure. Okay, so that's the important one. So with this simplify, with this also try to expand of this, try to expand the CL. How it will be the CL? CL equals to L by half rho V infinity square by S. For our most of the studies, we always see CL as it is convenient and it is a non-dimensional. We see the parameter CL in aerodynamics, or all aerodynamists see how it is the CL generating at that particular angle of attack. Angle of attack is also one kind of definition, I will let you know. And this is the amount, instead of the amount measuring the total amount of force, because it is easier to compare between one kind of wing to another kind of wing, or one kind of airplane to another kind of aeroplane, aircraft, whatever it is. So CL is the crucial parameter that aerodynamics need to understand. And let's see how this CL varies with angle of attack. What is an angle of attack? Angle of attack, suppose this is your airfoil and this is your fish stream. If you draw a horizontal line like this, and if you airfoil, if you join the front tip, this front tip to end tip, we call this as leading edge and this as trailing edge. Just join these two lines of a straight line. The flow, the angle between the incoming flow, if your incoming flow is horizontal, and the angle between this chord line, this line we call, whatever this straight line is called, we called as a chord line. So the angle between these two is the angle of attack, and the symbol is alpha. If you increase the angle of attack, the CL varies. And how in general it varies is, it will take this kind of profile. Okay, some aerofoils it takes this kind of profile. Some other airfoils passes through origin, the lift passes through the origin. But all the airfoils has the common characteristic that all these aerofoils will show a decrease in CL. This is your non-dimensional lift coefficient. A decrease in lift coefficient after some angle of attack. That angle of attack we call as stall angle of attack, alpha stall. So every angle of attack. You will see what are these types of aerofoils, why some aerofoils follow this kind of profile, like from here to here like this, and some aerofoils follows. What are these three different types of profiles of aerofoils and why they are following this kind of profiles? And next we will see how to resolve the forces on the aerofoil. consider an aerofoil like this, and this is your chord. If you have a force, axial force A here, and a normal force means force normal to the chord, normal force is the force normal to the chord. This is force N, and this is your axial force, and this is your normal force. So what actually these normal force is? Force normal to the chord of the airfoil and force in parallel to the chord of the airfoil. But lift is actually defined as, if this is your incoming flow, it is, suppose assume it is horizontal, lift is defined as the component of the force that acts perpendicular to the flow direction. If flow direction is horizontal, then the force that is acting, the amount of force that is acting perpendicular to the flow direction, that is what we call as a lift. And the drag is the amount of force acting parallel to the flow is called the drag force, and it is denoted by the letter D. So it is easier to measure the normal force and axial force, and it is necessary also to convert from normal force to axial force by using some transformation. How you can transform from lift, how you can find out the lift component and the drag components are by using this equation. L equals to n cos alpha, where alpha is your angle of attack, minus a sine alpha. This is how you can find your lift. And drag is n sine alpha plus a cos alpha. These are the two important equations that you need to remember for the entire course, like how you can transfer from the normal direction to normal forces and axial forces to the lift and drag direction. Okay, let's go to the sign convention that are using in present study, or it's normal if you find out any textbook of aerodynamics. If this is your airfoil, consider any two points on the surface A. Suppose this is your A and A dash. What is your sign convention is, let's consider the surface A, point A, very small portion, and draw a vertical line and horizontal line. The pressure force always acts normal to the surface at that point. This is your pressure force. And the skin friction force always acts tangential to the surface at that point. This is your skin friction force. If you measure your angle of this normal force in an anti-clockwise direction from your vertical line, this is your vertical line, and you are measuring your force direction in anti-clockwise direction. So this is minus theta. Okay. In the same way, from horizontal, if you are getting a theta by anti-clockwise direction of, if you are getting your tau by rotating in anti-clockwise direction, then that theta is a negative. If you do the same thing, same analysis for the point A dash, the things will be reversed. This is your normal force and this is your tangential force. From horizontal, you can see you need to rotate in clockwise, so it is positive theta, and from vertical you need to rotate in clockwise. This is also positive theta. This is your pressure force. Okay, so this is the important sign convention that you need to follow for all problem solving sessions. And then if you want to find out the small normal force acting at this elemental length, that is the d, yes, but this elemental length, if you want to find out what is the normal force acting at that point, the equations are like dnu equals to minus pu. Pu represents this suffix, this subscript u represents upper surface of the aerofoil, and dsu, this is a small elemental length on the upper surface, and that is cos theta, minus tau u dsu sin theta. This equation written for the point A dash, but this also applicable for the point A, because if you substitute this sign convention, whatever the sign convention we followed, Just try to substitute the sign convention, then you can see how these equations are suitable for the A dash or the entire surface. And the dAu equals to minus PU dSu cos, dSu sine theta, and then plus tau u dSu cos theta. So this is how you need to find out your elemental normal force and elemental axial force. If you integrate over the surface, if you want to know the derivation of these equations clearly, you can go through the lectures once again, you can find out these things. So these are very important to calculate the forces on any surface. This can be applicable. Okay, and then let's see, yeah, some standard formulations we have. With this understanding, we can say CL equals to L by Q infinity S. I already show you how the CL came as a constant or proportional to constant, and CD equals to, in the same way as how we derived for the lift, we can also say CD equals to drag by Q infinity into S. And in the similar way, we can also write the things for coefficient for the normal force is N by Q infinity S, and coefficient for the axial force, it's A by Q infinity S. One more thing that we need to mention is coefficient of movement. Movement coefficient is M by Q infinity into S into L. This L is the characteristic length. Generally, you can take as a chord length of this chord length. This is the length between leading edge to trailing edge. This is a usual procedure they take as a chord length. That is the coefficient of movement. So these are all the important equations, and few more things are, few more non-dimensional important coefficients are the skin friction coefficient, or skin friction coefficient. We can say this is due to the friction tau by, you can non-dimensionalize by Q infinity. Okay, this is how you can write the skin friction coefficient. And Cp, coefficient of pressure, also you can write as P minus P infinity, where P is the static pressure and P infinity is the pressure on the surface. P infinity is the pressure in the free stream. If we have a free stream here, and if this free stream means the incoming flow of air or water, whatever it is, so that incoming thing has some certain pressure. That pressure we call as a P infinity, that is free stream pressure. After it touching the body, at every location, at every point on the body, your pressure varies. That pressure we call as P. We denote that pressure as a P. So that pressure P minus P infinity by Q infinity, that is dynamic pressure. So this concludes your small equations and important formulations so far with respect to the aerofoil. If you now let's go to the entire aircraft, how the thrust is acting on the airfoil. The sample thrust equation, very simple form of thrust equation, we can write it as propulsion form of equation. We can also say as m dot MEV, that is mass flow rate of fuel plus air from the jet engine. The jet engine or the turbofan engine or turbojet engine that we see for the aircrafts, it will expel a certain amount of fluid continuously with some certain mass flow rate. That mass flow rate is we call as m dot v, and it is the exit velocity, the velocity at which those things are exiting is ve, and then m dot naught, the amount of mass flow rate of air or the fluid that is entering into the engine is m dot o, that we call denote with m dot o, and what is the velocity of that entering fluid plus the pressure difference at the exit times the area at the exit. This will give the thrust force. You can say also is a thrust force, the thrust force generating by the engine. Okay, so let's stop this discussion of equations or the recap of all the content in the week 1. Now we will see some important problems in we will see some important problems in this regarding these kind of equations what we have learned so far. So let's go to our first problem. This is our first problem. The first problem they are asking is, vortex shedding is an oscillating flow that takes place when a fluid such as air or water flows past a bluff body at certain velocities. Depending on the size and shape of the body, which of the following is or are the most suitable response or responses to this flow? They are asking something about the vortex shedding is an oscillating flow. Okay, they're asking something like a vortex shedding. Vortex shedding means if you have a object here, consider a cylinder of circular shape, and incoming flow is like this. If your flow is having number, then you can see the flow is curling like it curls like this. In the downstream, this will call as the downward direction we call as the downstream. In the downstream of the cylinder, we will see this kind of structures in the flow. This is called, we call as a vortex shedding, and it is oscillating. It has the nature of the oscillating nature. So what will happen if this kind of nature is there in the flow? Let's see the options. Vertices are observed near the rear portion of the body. Yes, vertices are observed. These are all vertices. We can see from the schematic image. So the vertices are observed from the rear portion of the body. Flow is never detached from the body. This is not possible. If the flow is detaching only, then we can see this kind of pattern, that is oscillating kind of pattern. And C, low pressure zones are formed in the separated flow region. Yes, vertices has a nature like a cyclone. You can imagine it as a cyclone. If there is a cyclone of rotating like this, then it is a vertex, and that creates a very low pressure. So this is also correct. Low pressure zones are formed in the separated flow region, and the ratio of lift to drag forces are high. This is not a correct thing, because lift force and drag forces are also oscillate as you vertices are also oscillating in the wake region, and that gives a different kind of profile, but not like a ratio is very high. Okay, so that is these two are the solutions of the question. Let's go to the next question. I just want to ask if you guys any doubts so far, because we will be seeing so many large lengthier questions and important one also in upcoming lectures. So I just want to ask you if you have any doubts. I will try to clear here now before going through those things. Okay, fine. Let's go to the other questions. So let's see this question. We have the question number 2. In this question number 2, what they asked, at an altitude of 53 kilometers from the Earth's surface. So there is an Earth surface here, and at an altitude of 53 kilometers, suppose at a point, let's take K, H equals to 53 kilometers. The mean temperature and of the atmosphere is 282.66 Kelvin. The mean temperature is temperature T equals to 282.66 Kelvin, right? Okay. And it is given that temperature decreases at a constant rate of 4.5 Kelvin per kilometer from an altitude of 53 kilometers to 79 kilometers. That means temperature given that constant rate temperature decreases at a constant rate from an altitude of 53 kilometers to it is decreasing. So let's say temperature profile with altitude. This is 53 and this is 79. This is decreasing at a rate of minus 4.5. The minus is belongs to the decrease in temperature, decreases at a rate of 4.5 to 4.5 Kelvin per kilometer, and then remains constant from 79 to 90, and then it remains constant from 79 to 90, up to 90 kilometers it is constant, and then increases at a constant rate. Again it is increasing at a constant rate of 4 Kelvin per kilometer up to an altitude of, let me draw overlap here, 105 kilometer. Up to 105 kilometer it is increasing. Now the question is, what is the approximate mean temperature of atmosphere at an altitude of 95 kilometer? The question is, they are asking approximately here T equals to question. They gave you H at these things, they gave you this here, T equals to 282.66 Kelvin, and here H also, you know, 53 kilometers. And now you have the lapse rate here and the constant temperature here, again lapse rate here. It is just a direct substitution of your lapse rate formula, and let's see how it will work. Just the question is lengthier, but you can see that given temperature at 53 and one more increase as a decreasing lapse rate on the constant isothermal and increasing lapse rate. Let's see how to solve this. So let's say this is known temperature, right? So known value system, then let's say it is H1 and T1, and if your H1 is equals to 53 kilometers and T1 equals to 282.66 kilometers, okay, then you have your first lapse rate, that is A1 equals to minus 4.5 Kelvin per kilometer, ready? Then which is valid only, remember that this is valid for 53 less than or equals to H less than or equals to 79. Then your A2 second lapse rate is plus 4 Kelvin per kilometer, and again this is also valid only between 90 less than or equals to H less than or equals to 105 kilometers. This is your second lapse rate, and the question is T4, the temperature at this portion. Say this is your T1, T2, T3 and T4. T4 equals to question at H4 equals to 95 kilometers. So we just note down all the given things. Then let's see how to find out that. We have directly, let's start from the second lapse rate. Second lapse rate saying A2 equals to T4. I want only the T4. T4 minus T3 by H4 minus H3. That is equals to, we have A2 equals to 4 Kelvin per kilometer. That is, you can write as a 4. But here there are two unknowns, that is T4 is unknown and T3 is also unknown. But you can find out that T3 by saying T3 equals to T2, because you have the isothermal region here. Since it is a constant temperature or isothermal region, your temperature won't vary. So that is why T3 equals to T2. So to find out T2, we again use this first lapse rate equation, that is A1. A1 equals to T2 minus T1 by H2 minus H1 is equals to minus 4.5. You can write your units, but let me solve this for the T2. If you simplify, you will get T2 equals to minus 4.5 times 79 minus 53 plus 282.66, okay, and that will give you your T2 value as 165.66 Kelvin. Okay, so now you have your T2 value, because you know your altitudes has H2 as 73, H1 as 53 and your T1 also. So now we have T2, and let's go solve for the T4. T4 is a direct substitution again in A2. T4 is equals to 4 times 95 minus 90. This is the difference in altitude, plus 165.66. That will give you 185.66 Kelvin. So the answer is D. Okay. Any questions in this? I will wait for some time for you note down. Let's so for 1 minute you can note it down if you, or else you can watch this video later on also. And if you have any doubts, please ask in this question. Okay, I'm proceeding further. Let's see the question number 3. This question is a bit typical one that you need to do some hands-on calculations like how to proceed for this. So let's start. A complete understanding of this question is, it takes some time, so please be attentive and try to follow up the step by step. Here the question is, we have a wedge here. This is what we call as a wedge shape. This triangle we call this as a wedge, and it is half angle. Its half angle is 5 degrees. As you, let me take the laser pointer. Okay, so here you have 5 degrees of angle, the half wedge angle, and it is at 0 angle of attack. That means the incoming flow is parallel to the height of this or chord line of this wedge, and the free stream pressure and density are, they give the free stream value and density also 1.01 times 10 to the power 5 Newton per meter square units of the pressure, and then 1.23 kg per meter cube. This is your units of density. So this correspond to the standard sea level conditions. The pressure on the upper surface and lower surfaces of the wedge are constant with distance s. So as you move from the S1 to S2, all this surface, they are seeing on the upper and lower surfaces, the pressure is Pu equals to 1.3. This is the constant pressure. There is no variation on the surface of the pressure along the surface. And what they are saying is, the chord length of the wedge is 2.5 meters. Okay, this is from leading edge to trailing edge, it's 2.5 meters, and they're asking, find out the total drag in the units of Newton. I will give you sample pointer options. Right, I will give you a simple understanding. So what kind of drag you can find out here? Drag is due to 1, pressure, and 2, skin friction or shear stress. Skin friction or shear stress. Okay, so one is the pressure drag and the second one is the skin friction or the shear drag. So let's try to understand the pressure, how it is varying on the upper and lower surface. Excuse me, Dada, please. So on the above surface, you have the pressure is varying constant from the leading edge to the trailing edge. This pressure is a constant pressure on both the surfaces, on the upper surface, also on the lower surface. But your skin friction, you see the equation of your skin friction here, this is varying with respect to the S. So the forces due to the pressure, I mean normal forces due to the pressure, will cancel out on the upper and lower surfaces, that we also see, we will see in the calculations. But the forces due to the skin friction on both the upper surface and lower surface, it won't cancel because they act in the direction, both the things will act in the direction along the flow. So this is your pressure drag and the skin friction, drag due to the pressure and drag due to the skin friction. Fine. But if you see the pressure difference between the downstream, that is backside of this, I mean, or the back of this wedge, you have the pressure 1.0 and 10 power 5, that is also free stream, and this is also the pressure difference. So still you have the component of the pressure, like this is a high pressure, it is 1.31 more than the pressure at 1.01. So because of this difference, you will get some pressure drag, and then you will get the skin friction drag, that is because of this equation. So It is a combination of both. And let's also don't forget the use of sign convention, how to solve this question. There's a sign convention. You just recall the sign convention I told you, like at two different points, how to use the theta sign convention, whether it's positive or negative. We will just apply that here directly. So it is at zero angle of attack, remember. So at zero angle of attack, your drag force is equals to your axial force. So I will just write the equation, that is d dash. This dash or this prime will represent your span is in unit length. I mean the normal direction length is unit. So that is equals to, you need to integrate the pressure and the shear stress from the leading edge to trailing edge times pressure on the upper surface into sine theta plus tau u cos theta dsu. Okay, and then this is for upper surface. You need to add the same thing for the lower surface, that is from leading edge to trailing edge. You will have PL sine theta plus PL cos theta, and that is ds lower. So summation of these two forces, you will get the drag force. So when you see, let's divide the pressure and shear stress components for solving this simply. Let me write the pressure components, that is leading edge to trailing edge minus pu sine theta dsu. Note that here minus is pu, the components of pressure, the normal force component of the pressure. Here you can see it is acting in the downward direction. If you take a component of it, it acts a downward direction on the upper surface. That is what this negative represents. Okay, that you can write as integral s1 to s2. That means I'm integrating from this part to this part. Integral s1 to s2 minus 1.31 times 10 to the power 5. This is the amount of pressure times sine of minus 5 degrees. Note that very carefully, this is a minus 5 degrees. Let me write it pointers help. So this is your minus 5 degrees. Okay, why it is minus, I will just give you the idea why I am writing minus here. So just use the idea again in your next calculations. This is your pressure direction, this is your surface. Suppose this is your surface at some point, take some point on the surface, on the upper surface, and this is your pressure direction and it is P, say. Now you need to measure the theta value. How you measure the theta value? You need to measure from the vertical axis at that point. This is your vertical axis and you need to rotate in the anti-clockwise direction. Since you are rotating in the anti-clockwise direction, this sign convention is minus theta, and your theta is the same as angle between this horizontal line to inclined line is same as this vertical line to the pressure. These two are the perpendicular lines. You can find out by using the geometry. You can understand by using the resolving of the geometry. So then you have your small elemental area dsu. This is your first component, and the second component is plus s2 to s3. What is s2? We calculated just from s1 to s2, that is done. Now it is s2 to s3. Okay, from s2 to s3, how you will write? This is again minus, because it is acting in the direction, this pressure is acting in the direction of opposite to the, that is, if you just say this is your x and this is your y. Let's see, it is now this pressure force is acting in the direction of minus y. Here it is acting in the direction of minus y. It is acting in the direction of, sorry, this is acting in the direction of minus x, and this is acting in the direction of minus y. Okay, so that's why this minus came. So that is amount of 1.01 times 10 to the power 5, and this is sine of 90 degrees, and this 90 is positive. Why? Because if you are standing at 2, okay, and you are trying to see the pressure value, how, in what direction you need to rotate at this point and perpendicular to the surface. This is your surface, and if you draw a perpendicular line, horizontal line here, you need to rotate in 90 degrees. Okay, so that's how, in the clockwise direction. Okay, you need to rotate in the clockwise direction, so that will give you your sine 90 degrees, and that is, next part is dsu. Okay, so solving this, we will get how to simplify this. You can simplify it with the available I can say with the available mathematics short term. We can find out this, as this is a constant value and this is also a constant value, and there is a sign minus 5, and this minus and minus will you get a positive value, and that is 14117.70. If you simplify, then just integral s1 to s2, because these two are constant, and it is dsu, and this s is varying linearly from s1 to s2. Then you will just get s2 minus s1, and the second part is 101. The same way, if you integrate 100.00 s3 minus s2. Got it? So on further simplification, how you can write this s2 minus s1? I can write the s2 minus s1 as, let me write the value, constant value before, by cos c is the chord length between the distance between here to here, that is you have the c equals to 2.5 meters. If you resolve that by using the trigonometry, you will get c by cos 5 degrees. Okay, then you will have 101,000.00. In the same way, if you resolve it again, this will comes to be c times tan 5 degrees. This is a simple trigonometry that you can apply. And now you also have the c value of c equals to 2.5 meters. Then just directly simply substitute the c value. You will get, let me substitute the value, and 17.40 times 2.51. Okay, then 101,000.00.22 equals to 6437.67 newtons. So this is your pressure drag, right? This is your pressure drag only on the upper surface. You see, we only did for the so far for the upper surface. We are yet to do the drag, sorry, here on the upper surface we are still need to do for the lower surface, the pressure component for the lower surface. Let me note it down, this value. This value, suppose I can note it down here, is the first value I got is 6437.67 newtons. I will just this will also I will erase. I have the data, I will write it later. Erase all in the slides. So let's go to the another component in the same way how we did for the upper surface. Let's see the pressure distribution for also in the lower surface. As we already told you, the pressure distribution in the upper and lower surface is same. The value you will get is also the same that we get for that you already got for the upper surface. But let's see with our calculations or with our sign convention, that is PL sin theta DSL is equals to integral S1 to S4. See, this is the point S4, that is S1 to S4 you are integrating. So S1 to S4 times 1.31 times 10 to the power 5 times sine of 5 degrees. This is a positive 5. just apply the sign convention that I already shown you how this positive or negative plays with the surface and the direction of your rotation. If you apply the same thing, then you can see this is a positive 5 degrees, and then your small elemental area DSL. Okay, and then another component you have is from surface S4 to S3. Okay, from S4 to S3, what you have? 1.01 times 10 to the power 5 times sine of minus 90 degrees. Just apply the same principle that we did already, then you will get this format. And again, you need to take out the constant values out and integrate the surface. Let me show that. Yes. Yeah. So how will you take out that? You will get again 11417.40 times S4 minus S1 plus 101,000.00 times minus 1 S3 minus S4. Your constants S3, S4, as it is obtained by after integration, this is integral ds. If integration and differentiation is cancelled out, you will get, I'll just apply the limits, that is S3, S4, here that is S3, S4, and then here it is S1, S4, S1, S4. Okay, so as we seen earlier, like how we can transform this S4 minus S1 with respect to the chord, with respect to this value. Let's apply the same principle again, that is 11417.40 times C by cos 5 degrees, that is the distance, plus 101,000.00. This is your minus value. Okay, this is your minus, and then you will get C tan 5 degrees. Now substitute your C value. You will have 11417.40 times 2.51 minus 101,000.00 times 0.2 to substitute your C value, and then you will get these values. This will give you again 6437.67 newtons. See, this value is same as we get earlier for the upper surface when we are doing the pressure integration on the upper surface. So just find out this, recall that upper surface pressure value. So now we have the drag due to the pressure on both upper and lower surfaces. We need to now find out the skin friction drag. How you can find out the drag due to skin friction? Let's see. In the same way as we did for the upper and lower surfaces, and in the terms of the pressure, let's apply for the drag. Tau u on the upper surface, that is cos theta dsu. We only need the tangential force in the direction of along the axis. So that will give you S1 to S2 500 s to the power minus 0.25. Here from the equation we are writing this. Okay, you see, as along the verge the shear stress is distributing and it is decreasing, and that's what we are just writing here. Then the cos of minus 5 degrees dsu. Got it? This, if you write it, see, we are not taking the S2 to S3 as because S2 to S3 is not in the direction, it is completely in the perpendicular plane of the axial direction. So the force on this plane due to the shear stress is in vertical direction. So vertical direction like this. So it does not contribute any axial force. So that's why we are not considering that. So let's see, if we simplify this equation, 498.10 times S2 power 0.75 minus S1 power 0.75 by 0.75. So this is your simplification. Again, we need to apply the same thing, like S2 minus S1 power 0.75 you have here by 0.75, and then you need to convert this S2 minus S1 again with respect to your chord length. How you can convert? By using the simple basic trigonometry. You can write it as 498.10 times C by cos 5 degrees, right? 0 power 0.75. Okay, times 1 by 0.75. You just separated this part out and then you simplified with respect to equation you have based upon the trigonometry of this wedge, and then you can write it as 498.10 times 1.99 times 1 by 0.75 is equals to 1321.63 newtons. So now we have the shear stress on the upper surface. This is the value on the upper surface. Let's try to calculate the value of the shear stress, force due to axial force due to the shear stress on the lower surface also. Let me clear this. Yeah, it is all linked. The same way as we calculated the shear stress, force due to shear stress on the upper surface, let's calculate on the lower surface. From the leading edge to trailing edge, tau L cos theta dsL, this is the lower surface, you will get integral S1 to S4 and 500 s to the power 0.25 times cos of minus 5 degrees. Okay, and then you will have dsL. Again, just substitute all the values and simplify this. You will get 498.10 S4 power 0.75 minus S1 power 0.75 by 0.75. Okay, you can further simplify it as 498.10 C by cos 5 degree 0.75, right, times 1 by 0.75. This will simplify. On simplifying further, you will get again the shear stress is same as on the upper surface, that is 1321.63 newtons. So now we solved for all the axial forces because of pressure and shear distribution on the entire surface. So let's sum up all these values. You will get d dash equals to 6437.67. This comes 2 times because on the upper and lower surfaces, and the same way 1321.63, this will also 2 times. So the total drag is 15518.60 newton. So your answer is answer C. This is a lengthier question just for your exercise to understand the entire pressure distributions around the wedge and to apply the sign convention for your complete understanding of the basics of pressure and shear force distribution and their respective for calculation with your available data. Okay. So now let's go to the, I just want to ask any doubts so far in this question. Okay, if no doubts, we will proceed further. Let's go to the question number 4. It's the question we have here asking about it is assumed that, okay, it is assumed that, let me have the leisure. It is assumed that the standard sea level temperature T infinity is 288 Kelvin and the velocity of the free stream V infinity is twice the sonic speed. They have given that temperature is 288 Kelvin, and the velocity of the flow, free stream flow, the incoming flow on the surface is V infinity, which is 2 times the speed of sound. Sonic speed is means the speed of sound at that corresponding location. So the velocity is twice the speed of the sound. So if the sonic speed is given by the equation of the sonic speed is A infinity equals to square root of gamma RT infinity, where you know all these values as gamma is Cp by Cv, that your ratio of specific heats, and R is a gas constant, and T infinity that you already given. The question is, what will be the drag coefficient for the same problem as mentioned in question 3? We just solved the question 3 and the amount of drag also we obtained. If that is the amount of drag, then how do you calculate the drag coefficient in the question 3? And then they given some constant. Let's see how to calculate this. So they are asking what is the drag coefficient for that problem. We know the drag coefficient CD equals to D by half rho V infinity square times S. Okay, so this is your drag coefficient D by half rho V infinity square S. We have the density. No, we don't have the density here. We have the velocity. No, we have to calculate the velocity also. We have the S. Yes, S is the planform area that we can calculate by the given geometrical parameters in the previous question. Let's first calculate the V infinity. V infinity that we have is information is 2 times of A infinity, and A infinity equals to 2 times of square root of gamma R T infinity. That is, if you simplify and solve this, just substitute the values. Sorry, you will get 287 times 288. This will give you 680.34 meters per second. Right now, the second question is you need to find the density. How you can find the density? Density you can find out by using the P equals to rho RT equation. And you have the temperature here 288 Kelvin, and you have the free stream pressure. Just recall from the free stream pressure of previous class, sorry, previous question. It is, let me show you the previous question. Just a minute. Yeah, here. You just take the pressure from this location, and you can substitute those two values in that equation as you have, sorry. As you have the pressure and temperature and R, you will get rho equals to 1.23 kg per meter cube. Fine. So use this density value, you can find out the equation. So now we have all the values, where S is just your chord length, because you have the unit length, as we already seen. S equals to chord length. What is the chord length? The planeform area. If the area that you are seeing, if you see the wedge perpendicular, that means on the top view of the wedge, from the top view side. So S equals to chord length C into the span is in unit value. So you say it's S equals to C into 1. Then substitute all these values here. You will get you have the total drag of 15518.60 newtons by what you have the velocity as half, and the it's substituted the half, and the density is 1.23, and your velocity is 680.34 square, and your surface area is chord equals to 2.5 meters. Then if you simplify this, you will get CD equals to 0.02. Note that CD drag coefficient is a non-dimensional one. There is no there are no dimensions for all these coefficient parameters. Okay, so any questions? Fine, let's go to the next question. Here is a question that from the study level flight, we already seen the study level equations flight in our introduction at the beginning of this class. and let's see what is the question of this in this point. Let's consider an airplane in study and level horizontal flight as illustrated in the figure. So in the study level flight, we should balance the forces by thrust with the drag and the lift with the weight. Okay, and for this case, the weight W acts vertically downwards, yes. The lift L acts vertically upwards, yes. Perpendicular to the relative wind V infinity, this is your V infinity. Perpendicular to it, the lift is acting. For this aeroplane flying at a given altitude, W is the weight of the aeroplane, rho density of the air, and S is the span of the wings. I mean the planform area. If you see the wing from the top view like this, the area that you will see of the wings, that we call as S, that is the planform area, are fixed values. Those are not variable. So yes, weight we can take is approximately constant, and rho and S. What is the expression for stalling velocity if CL max denotes the maximum value of the lift coefficient? It's a very interesting question that you can see the interesting things of how to use this CL max and find out the maximum velocity, or sorry, minimum velocity that a flight requires. Suppose, let me consider CL versus alpha plot again. This is your CL versus alpha plot. This is your alpha star, where you will get maximum lift coefficient. Okay, this is your maximum lift coefficient condition, and the angle of attack is corresponding to alpha star. Now let us consider what is the actual equation of the CL. CL equals to lift by half rho V infinity square S. If you just recall the equation of the CL from our previous introduction content, this is the equation of the lift. CL equals to L by half rho V infinity square times S. So now in this study level flight, what is your L? L equals to W. So let me just substitute L equals to W. CL equals to W by half rho V infinity square. Yes. What are your constants? Your constants are, let me take out your constants. CL V infinity square is equals to, I will just write it as 2W by rho ES. Okay, so this is all your constant values, so which I can write it as a constant some value K. If I'm writing that value as K, and CL V infinity square equals to K. Okay, you should, if you want to maintain the study level flight, you should maintain your CL and V infinity. These two can be variable. V infinity means it's nothing but the flight velocity, the velocity at which flight is moving at that particular altitude. And the CL means the non-dimensional lift coefficient acting on the wing or the flight. These two, product of V infinity square and the CL, should be constant. It should not vary. Then only you can maintain your study level flight, right? So if you are maintaining these two parameters, like how you will maintain? Suppose if I am maintaining the CL has a value of suppose say 0.5 here. My CL value is 0.5 at this location, and the say angle of attack is 6 degrees, 6-degree angle of attack, and the CL is 0.5 here. At this 0.5, I will write some velocity of, I'm just assuming some velocity of 100 meters per second, and I'm squaring it. That will give me some constant value. If I need to maintain my CL at the maximum value, CL denotes the maximum value. If I need to maintain my CL at the maximum value, what it means. The CL maximum, let's consider it as 1.2 is your maximum CL at alpha equals to 14 degrees. Okay, at alpha equals to 14 degrees, assume this is your CL max. Now your CL increased to CL max. To make this value as a constant means this product of V infinity square and your CL max, to make this value as constant, the V infinity should decrease to say 50. Suppose just some, it's not a correct proportion, but I'm just, for your example, I'm just saying it's a 50 square, something like that. So to maintain this value as a constant, your velocity should decrease, but you cannot go any further CL because it is already reaching the stall velocity. That means as you are increasing your CL, as you increasing your CL, you need to decrease your velocity to maintain the steady level flight. So at maximum CL, the velocity of the flight is very minimum. That means in another way you can also state as the minimum velocity required for the flight, the minimum velocity required for the flight to maintain steady level is the velocity corresponding to maximum lift coefficient, that is CL. Right, at the maximum CL you can maintain your infinity. So I will just substitute the same thing in the CL equation. CL max is equals to lift by half rho V. I will say instead of V infinity, this is a V stall because you are already substituting your CL max, that is corresponding to the stall velocity. So minimum velocity, if you reduce your velocity less than this, then you will experience a sudden drop of lift. Okay, then you go yes value, and remember that L equals to W. Then if you simplify or rearrange this equation, you will get V stall equals to 2W by rho infinity is also fixed in S, and CL max. So this is the solution of this problem. So that's how you need to solve for the minimum stall velocity of a flight. So any questions in this? Any doubts? Okay, let's move on to the next question. Okay. The question number 6. In this question we have an executive jet plane. Let me take the laser point. An executive jet plane is flying at a speed of 791 kilometers per hour, okay, at an altitude of 10058. Let me take the question number 6. Okay. At an altitude of 10058 meters with an air density of 0.41 kg per meter cube. Okay. And then the weight of the wing planeform area of the plane are 68030 newtons and 32 meters square respectively. At cruise, the drag coefficient is 0.015. The lift coefficient will be, this is the question. They gave the drag coefficient for use for us and asking a lift coefficient with the given data. Let me take a pen. Okay. So what is our lift coefficient? Lift coefficient CL equals to L by half rho V infinity square S. What are the values we have? Do we have lift? No, but we have the weight of the wing, weight on the wing. Okay, the weight of the total aircraft, that is L equals to W. So and then we have the density. Yes, we have the density. Do we have the V infinity? Yes, we have the V infinity. And do we have the span area? Yes, that is 32 meters per second. All the data is given readily and we can substitute it. That is 66030 by half of the air density is 0.41. V infinity, see that V infinity is in kilometers per hour. You need to convert that into meters per second for the substitution, as all the remaining are in meters and seconds of units. That is, if you convert that, you will get 219.72 meters per second. Okay, this is your V infinity value, and then substitute it. 219.72 whole square by S, the span area, that is 32 meters square. You will get the CL value of 0.21. This is a non-dimensional one. You don't have any units for this. Okay, that is the sixth question. Let's go to the next one. The question is problem 7. For the problem given in question 6, the lift to drag ratio will be. The lift to drag ratio is asking, that means L by D ratio. Do we have the drag value in the previous problem? Let's see. We have only the drag coefficient, but we don't have the drag value. But what we can do is we can multiply this CD into half rho V infinity square. As we have all these values, then we will get the drag value because they give the drag coefficient. Or else one more thing we can do is, let me show you how to do. This is the lift coefficient. Lift coefficient I can write as CL by half rho V infinity square into S. In the same way, CD also I can write as, drag also I can write as CD by half rho V infinity square into S. If you simplify this, L by D is nothing but CL by CD. What is your CL? Let me see. CL is 0.21 and CD is 0.015 by 0.015. What you will get? This is question number 7. You will get CL by CD equals to 14. This is also called as aerodynamic efficiency. The ratio of lift to drag is called aerodynamic. You need to keep it in your mind, and it will be very useful parameter. If the drag is very much less and the lift is very much high, your efficiency will also goes high. So it is always a matter to, it is necessary and it is very useful technique if you find some technique to decrease the drag to increase the overall aerodynamic efficiency, so that we need very less power to travel in the flights or the any aircrafts. So let's go to the next question. In this question, now we have at sea level, let me read the question. What is this? Pointer options, laser, right. At sea level, the pressure is 101,325 Newton per meter square, yes. And the temperature is 288 Kelvin, yes. These are the standard pressure and temperature. And the lapse rate, it is 0.0065 Kelvin per meter. We already seen this is the lapse rate of 6.5 Kelvin per meter. And you should understand whether it is a decreasing lapse rate or increasing lapse rate by looking at our previous understanding of the standard temperature table. You can say it is a decreasing lapse rate. The pressure and temperature in the troposphere at two distinct elevations. See, the pressure and temperature in the troposphere at two distinct elevations are related as this equation also they gave clearly, that is P1 by P2 is T1 by T2 over G by LR. You need to remember the equations. So where G also the constant value or also the constant value. The question is at 10,000 meter the pressure and density are respectively. The question is just they are asking the pressure and temperature at 10,000 meters or it is a 10 kilometers. Let's start our question. The given value, with the given values we have P1 equals to 101325 Newton per meter square and T1 equals to 288 Kelvin, right? Your lapse rate L equals to 0.065 Kelvin per meter. See, the unit should be very careful. This is, sorry, Kelvin per meter. So let's try to substitute in this to get the equations required for, whatever the parameters they asked for. They asked for the pressure and density. Suppose you this is the sea level and this is the 10 kilometers height. You have the temperature in the standard atmosphere decreases. If you see the profile, temperature, the height. So this is the temperature, this is the height, and this is negative lapse rate minus here. So your lapse rate is a -1. Okay, so your temperature should decrease at 10 kilometers altitude. This is your 10 kilometers altitude. So as you go high, your temperature should decrease. That is the point here. And how do you find out your temperature? Like you already have the T1. What you need to find out is you need to find out T2. How can you find out the T2? Let's see with the available equations. That is T2 equals to, or I will write the lapse rate equation at the first so that you can understand why I am writing for the why I am writing this for this T1. Pointer, yeah. T first is T2, yes, T2 minus T1 by H2 minus H1 is equals to minus 0.0065. Substitute all the things in meters and Kelvin, then you will get T2 equals to minus 0.0065 times 10,000, because the altitude is 10,000 meters. H2 minus H1, they just gave the difference, and then you will have T1 as how much? T1 is 288 Kelvin. If you simplify this, you will get T2 equals to 223 Kelvin, right? This is your T2. And now I have in this equation T1 I have, T2 I have now, and P1. Is there a P1? Yes, this is your P1. Understand? This is your P1 you have. G is a constant, L also lapse rate you have, R is also a constant and is a given. So just substitute all the values to solve for the P1 and solve for the P2. P2 you will get as P2 equals to 101,325 by, this is the ratios of temperature, that is 1.2915. This is the ratios of temperature, and then you substitute G by LR and it will give you, it should be a -1 as your L is a negative, and that is 5.2561. You will get P2 also a reduced value, that is 26,411. Yeah, 26,411.4795 Newton per meter square, right? So now this is your reduced pressure, because as you increase the temperature is decreasing with altitude, your pressure should also decrease. And then they also asked what is your density at that point. How to find your density? It is the direct relation of perfect gas equation or the characteristic gas equation. To substitute your values, that is the P equals to rho RT equation, then rho T equals to P2 RT2, then 26411.4795 by 287.14 times 223. Got it? That will equals to 0.4125 kg per meter cube. So this is your density value. Fine. Let's go to the next question. Any doubts so far? Any doubts? Okay, let's move on to the next question. So in your next question, you have a problem of understanding the atmosphere that you have learned the concepts so far. And here this understanding requires more application point of view, like how better you understand your standard atmosphere, that much easier it is to understand this question, and also to see the effects of or the importance of the standard atmosphere. Consider the atmosphere at rest, that is at H1, the atmosphere at rest, and a tiny element of air is suddenly displaced a short distance upwards, a very small distance of element, a small element. This is suddenly displaced a short distance upwards, okay, and it displaces it to the distance H2. Which of the following option is the correct option? They just gave the details of the pressure, temperature and density of the tiny element, and the corresponding surrounding pressure, temperature and density at that height H1, and this mass is displaced to this position at the H2, and it acquired the density of ρ2 dash, P2 dash, T2 dash, and the surrounding temperature has ρ2, P2 and T2 temperatures. Okay, so here the thing is they are asking us to understand what is the use of, or sorry, how this how this will give you a figure of the four options, how you can what are the comments you can make based upon this figure. Like the options, let's see what they are posing is: the displaced element may remain in its new position. That means if the element standing here, it will go to the new position and it will stay here, okay. And then the second option is the displaced element may tend to return to its original position. That is, it goes up, this displaced element will goes up and it will come to the original position, that is it goes to H2 and it will come back to the H1, okay. And the third one is the displaced element may continue upwards. That means if it is starting from here, it is going to H2 and it will continues to goes to the higher positions. It won't come back to the rest position. So this is what the question is. So, and the question D is nothing can be said in this regard. So I just need to give some conceptual understanding before explaining which how this particle, I mean without any good information of this, like we have another sufficient some information like E equals to K rho power n, this is the standard law that we follow, and then n equals to 1.235 in the international standard atmosphere troposphere, and n equals to 1.0. Only this much of information we have, and they're asking what would be the particle reaction if it is going to this height, whether it is stays there or it will come back to the same position or it will displace continuously. I need to give some conceptual understanding before solving this or before theoretically understanding the behavior of this particle. I also told at the beginning of the class, the standard atmosphere relations or the standard atmosphere table will help you a lot to understanding this displaced mass behavior in the atmosphere by like any, assume this is a chimney smoke. If the smoke coming from the chimney or it is heated up, it has some temperature more than the atmosphere. So whether it will goes up or whether it goes down, those things also we need to understand, whether it is dispersed in the uh, atmosphere or not, those things also we need to understand and can be easily understandable by this figures, okay. So let's see how it will work. The small conceptual thing that I need to give you is to state some particle at equilibrium or not. There are three things: stable particle and neutrally stable particle, and three, unstable particle. How you can say what are these three things? These three things have the same definitions of the options they're given here. One is the stable particle. In this stable particle, if you have an element here from the point h1, this will displace to the point h2 and it will come back to the point h1. If it comes back to the point h1, then we called as stable particle. That is option 1. If it is going to the some particular height, or it is going up or down and staying there or not coming back, then we can say it is a neutrally stable. If it is moving to up or down and continues moving in this direction, then we can say it is a completely unstable particle. Okay, so how you can define this by a particle is stable or not? We can characterize it by two things. One is the density ratio of the density ratio of particle to the surrounding atmosphere, and the second one, density, no, it's not a density ratio, it's a lapse rate definition. Let me erase it. Yeah, the second one is a lapse rate. Okay, the lapse rate difference or lapse rate ratio of lapse rate difference. Suppose I will say it is easier to understand from the density ratio of a particle to the surrounding. Suppose if the particle is here and it is having a density of ρ1 and atmosphere is having a density of ρ2, and the ratio of ρ2, I mean the density of the atmosphere is greater than the density of the particle. The density of the particle is less and the atmosphere, so I will say it is ρ atmosphere. Atmosphere density is more than the particle density. This is particle P. Then what will you get? You will see this particle continues to float until it reaches some atmosphere where it can matches with its density particle. So it continuously goes up. Or if the particle density is same as atmosphere density, then the particle stays there. That is neutrally stable. If the particle density is high, if the particle density is high than the atmosphere, then you will get a low or decreasing. The particle will tend to decrease to the downside. Few minutes ago, the particle will move to the down in the atmosphere. This is what the first thing that you can conclude whether the particle is stable or not. And the second thing is by looking at the lapse rate. Suppose in the atmosphere, if the particle is moving from h1 to h2, and if it is moving from h1 to h2, there can be some choices like it can release the heat, or it can take the heat from the atmosphere, or it can neither release or take the heat. So if it is not taking any heat, then that process we called as adiabatic. Even it is moving from here to here and it is not taking any or releasing any heat, then we can call it as a adiabatic process. And in this adiabatic process, there is no heat transfer, that is Q equals to 0. If the Q heat transfer is 0, then we can say it follows some particular adiabatic profile or the gamma, some particular relation, that is P equals to K rho to the power gamma, where K equals to 1.4. In this adiabatic process, the relation is P equals to K rho to the power gamma, where gamma equals to 1.4. This is the relation. If process is adiabatic, the pressure and density can be related with this equation, with this kind of index. So in this index can also be related to the lapse rate. There is a relation between the lapse rate and the index, this n index, where this n index is the crucial one that relates the pressure and density. This can be related to the lapse rate, and this lapse rate can govern whether the particle will goes up, whether it is stable, unstable, or neutrally stable. These concepts we will also learn in our next classes on the next live session. As we are running out of time, I will stop here. If anyone has doubts, you can clarify your doubts in 1 or 2 minutes. I will continue this class from here in the next session. Any doubts? Shamhita? Tanmay? Any doubts so far?
No, sir.
Okay. Ashwin? Nasruddin? Okay, thank you. I will end this session now. Yes, Ashwin?
Yes, sir. Sorry for joining late.
Okay, no issue.
Sorry for joining late. Can we have the session a little bit towards the end or on Saturdays? It's a humble request because I'm a working professional and it would be better if we have some timings changed. Is it possible?
Uh, no, Ashwin, it is not possible because it is already decided by many courses are handling by the NPTEL team. So if one course
Mm-hmm.
is fixed at a particular time, it's very difficult to rearrange by them. So it's more or less not possible. I can say it's not at all possible. But you can watch this recording. I will. You can follow this recording by. You can type my name Gangadhar Pinapatrani. I will just chat also. You can find
Okay.
it these recordings in my YouTube channel, or those
Mm-hmm.
same links you can find out uh, by there. We will share. We will share. NPTEL team will share with you soon.
Okay. Okay, sir. Thanks a lot.
You can follow. I think you just received any chat message.
As of now, no.
Okay,
One
maybe it's
second.
not possible if you directly joined from the browser. So
Uh-huh.
you can find it Gangadhar Penapadran. Type my name just in YouTube. You can find out this, or else they will share the link soon. I will post this in the group discussions of the NPTEL
Mhm.
Gmail group discussions are there, right? I will post there.
Okay. Okay. Sure, sir.
Okay.
Thank you.
Okay. Thank you, Ashwin. So have a good day, everyone. Thank you for joining. See you in the next session.